Hey everyone, in this video we're going to solve this truss that you see on the left. The way that we're going to do this is, number one, we're going to find the support reactions. We're simply going to remove the pin joints. Pin joints only have force reactions, there's no moment reaction. And then we're going to use the equilibrium equations in terms of force and moment, sum of force and sum of moment. To find the support reactions. After that, these are two force members, so we'll use the support reactions to find the internal forces. And then we're asked to figure out if the structure can safely support the 30 kilonewton load, and the material of which it is made is W350 steel, which has a yield strength of 350 megapascals. And lastly, we're asked to calculate the diameter of the tension rod so that it has a safety factor of 2 if it's made out of aluminum with a yield strength of 240 megapascals. So step number one is to find the support reactions. And the way that we do that is we remove the supports, and on the free body diagram we will replace them by forces. So this is going to be, let's call it AX. Let's put a little coordinate system here. X, Y, this is AY. So that point is A. This point is B. There is a 30 kilonewton force in the negative Y direction. And so we have, this is point C, so this is CX, and this is CY. It doesn't matter in what direction you choose to draw these forces. If ever you find a negative value when we do the calculations, that just means that they're in the opposite direction of that which you drew them. So number one is we're going to take the sum of the moments by A, and so we're going to have Cx multiplied by 0.6 meters. And I just need to, so yeah, counterclockwise is positive. So there's a counterclockwise moment generated by Cx. So AX and AY don't generate a moment by A because there's no arm or distance from it. Lever arm, I think, is the right term. The other thing that we have is a negative moment of 30 kilonewtons times 0.8 meters. And that is equal to 0. It's equal to 0 because it's not moving, it's static. So Cx is equal to 30 times 0.8 divided by 0.6, and that's equal to 40 kilonewtons. We're going to take the sum of the forces in the x direction, and so we have Cx plus Ax, and that's equal to 0. So that means that Cx is equal to the opposite of Ax. What if we took the sum of the forces in the y direction? We would have Ay minus plus Cy, sorry, minus 30 is equal to 0. We can't do anything with that because Ay and Cy, there's no way to isolate anything. Cx is equal to minus Ax, but we already have Cx. So Ax is equal to minus 40 kilonewtons. Okay, so we could try to take the moment about B, and we would get the AY term times 0.8 and CY times 0.8. I'm going to spoil it for you, it's not going to work, but still, let's try it. The moment about B, so that's AY times 0.8 or minus AY times minus AX times 0.6 minus CY times 0.8, and that is equal to 0. If we substitute A sub x by minus 40 times 0.8 minus 40 times 0.6 cy times 0.8, 0. What we'll end up with if we isolate A sub y is A sub y is equal to 30 minus cy. Now if you substitute this into the previous equation, what you would get is AY plus CY minus 30 is equal to 30 minus CY plus CY, minus CY is equal to, I forgot. Let me rewrite that. So A sub y is 30 minus C sub y plus CY minus 30 is equal to 0. Well, what we get is 0 equals 0. So we need to find another way to get the AX term. Alright, well that's not really a problem because the individual components are in equilibrium. So we can take a force balance of the CB member, and we would also have some reaction here and also there. So that is 30 kilonewtons. So let's take the moment at B. If we take the moment at B, we will get an expression for CY only, right? Okay, so if you take the moment at B, I didn't give these guys any names just because we're not going to use them since we're taking the moment at B, but you know, they're there. So the moment at B is equal to minus CY minus CY times 0.8 is equal to, am I right in saying this? Let me make sure. Yeah, okay, so right, that's equal to 0. So CY is equal to 0. Let's start circling our answers so that we don't lose track of them. We have CX is equal to 0. We have A plus AY plus CY minus 30 is equal to 0. What else do we have? We have CY is equal to 0. Yeah, so if CY is equal to 0, then AY is equal to 30 kilonewtons. We're going to highlight that as well. Okay. So what else do we have? There's A sub y, which we have C sub y, Cx, and Cx is 40. Yeah, we have all of them. I just forgot to highlight this guy. Okay, so I'll just put a check mark. Cy is 0, Ay is 30 kilonewtons, 30, and A sub y minus 40, A sub x, sorry, and C sub x is 40. Okay, cool. So now we need to find the internal forces. Well, that's pretty simple because all we need to do really is to, at point B, we have a force going along the AB member, and then we have another force. So let's say that this is force AB, this is force BC, and this is 30 kilonewtons. There's an angle here, and the angle is equal to the inverse tan of 0.6 over 0.8, so just 6 over 8. And that's equal to 36.8699. I always keep 4 significant digits, or 4 decimal places rather, when I calculate angles. Okay, so this could be redrawn, and maybe I'll be clearer. This is point B. So at this point, I have force going along the two force member, and another force here. This is FAB. So yeah, I should actually rewrite those. Okay, and then force BC. Okay, so let's draw the force triangle. You don't have to do that. No, when you get used to it, don't bother. But so theta. This is FAB. This is 30 kilonewtons, and this is BC. Yeah. So FBC is equal to 30. Yeah. Is what I'm saying true? So let's say rather FAB. I'll just write the actual thing. So sine theta is equal to 30 over FAB. So FAB is equal to 30 divided by sine theta. And so FAB is equal to 30 over sine of 36.8699, and that is equal to 50 kilonewtons. Okay, so FBC, we're just going to use the Pythagorean theorem. So it'll be the square root of 50 squared minus 30 squared. And, well, actually that's a 3, 4, 5. That's a Pythagorean triangle, so that's 40. Yeah, just 40 kilonewtons. Okay. Let's highlight those results. So these are the internal forces. So what next? Can the structure safely support the 30 kilonewton load? Sure, let's check it out. So the BC member is in compression. We're not going to look for if it's buckling or not, but let's just calculate the stress in it. So the stress in BC is equal to FBC divided by the cross-sectional area of BC. So FBC is, actually let's write C for compression and T for tension. Okay. Actually, I made a small mistake here. This should be in the other direction. The reason is that when you draw the triangle, you need to go from head to tail to head to tail. Yeah. Okay. So BC is in tension. And we have compression for AB. All right, so FBC, that's 40,000 newtons divided by pi over 4 times the diameter squared, and the diameter is 50 millimeters. And that'll give you 40,000, 20.4 megapascals. So that's clearly okay. I mean, we're so far from the yield strength that we don't even need to bother. What about AB? Well, that's FAB over the cross-sectional area AB. And so that's 50,000 newtons divided by, the diameter is 20 millimeters. So that's pi over 4 times 0.02 squared in meters. And what you'll get is 159 megapascals, so 10 to the 6. Okay. So let's calculate the factor of safety, which is the yield strength, or sometimes they write it as sigma allowable on the applied. So we said that it's made out of W350 steel. So 350 divided by 159 gives us a factor of safety of 2.2 greater than 1 equals safe. Okay, in reality it's slightly more complicated than that. You need to check for buckling because it seems like the member could be a long member, but for the sake of this problem, let's just say that it passes the test. So let's highlight that result. Okay, so the next and final step is to find the required diameter of the tension rod so that the factor of safety is equal to 2 when aluminum has a, well, rather, it's made out of aluminum and the yield strength is 240 megapascals. This part of the problem is useless. It could be, tension or whatever. It doesn't matter. The result is going to be the same because we're not considering length. So let's forge ahead. So the factor of safety is equal to yield strength divided by the applied constraint. So that is 240 times 10 to the 6 divided by, and the reason why I put 10 to the 6 here is because that's so that my units are newtons per meter square. And the applied stress is the force over the area. So we know that the force in let's say that we're going to use the one in AB. So I'll actually rewrite it and say that yeah, in AB. So that the force in AB is 50,000 newtons. Divided by the area, which is pi over 4 times d squared. And we said that in the problem, it says that that needs to be equal to 2. Not a problem. So if you isolate the diameter, you'll get the square root of factor of safety times the force times 4. Pi is under here, and you'll get 350 times 10 to the 6 here, square root of all that, and what you'll get is 19.13, 10 to the minus 3 meters, or 19.1 millimeters. So let's highlight this guy. And just a quick note, it needs to be at least, at the very least, it needs to be that. So if you increase that area, then the applied stress is going to become smaller, and so the safety factor will rise. That's it. The PDF worksheet is in the description below. Thanks for hanging on.